All right, good morning, everyone. It's my pleasure today to introduce Michael Antonelli, assistant professor at University of Houston. Michael and I overlap a little bit in Zurich, so it's nice to see him again after a couple of years. So Michael is Canadian. He did his studies in... Where's the flag?
I'm from Edmonton, too. Yeah.
That's where he did his undergrad, and then he was actually here in DC for his master's at University of Maryland. At the time, he briefly visited Carnegie with a nut. Then he moved on to Berkeley for his PhD with Don DePolo, and then he traveled to Europe to IPGP, so the Institut de Physique du Globe in Paris, for a postdoc with Fred Monnier. And then he won a postdoctoral fellowship and moved to ETH in Zurich. And finally was appointed assistant professor at University of Houston 2 years ago, roughly. Michael is, I guess, the global expert in calcium isotopes. And so today we're going to hear a little bit about that. Thank you.
Thank you. Okay, yeah. So I don't know if... How about now? Okay. I'm really more calcium isotopes in high temperature things. I think there's people who are more expert than I am in lower temperature things. So anyway, today's talk is kind of going to be an overview talk. I'm going to keep it fairly accessible, so there'll be some fun analogies throughout. And basically talking about calcium isotopes in igneous rocks. And so that like volcanic rocks, different kinds of things that were magmas before. And people want to use calcium isotopes to be able to trace recycled marine carbonates within igneous rocks. That's kind of the overarching theme of the talk. Oh, there we go. Okay, calcium. Many of you know it, right? Many of you have calcium in your bodies. And you can supplement it with, pure powder, like high percentage of calcium in calcium carbonate. It's actually fantastic because the molar mass of calcium carbonate is about 100 grams per mole. The molar mass of calcium is 40, and so it's 40% calcium. Right? This is blue limestone. It looks like amazonite. Right? I don't know. A joke for the geologists. So the overarching question of this talk is it possible to use calcium isotopes to trace recycled marine carbonates in the mantle and in crustal magmas? So this is kind of a schematic of this. Here's a sand castle made of shelly white sand, right, calcium. It looks like this under the microscope. And people think this falls to the bottom of the ocean and goes down, where it can be remelted and potentially come back in volcanoes, right? So this is what we call the deep carbon cycle. So this is the surface carbon cycle, the deep carbon cycle, and maybe it keeps going round and round like this. Okay. Okay. So I'm going to assume that not everyone here is an isotope person, although I know everyone has calcium. So we're going to start with like, what are isotopes, right? So isotopes are a version of an element with a different number of neutrons. I think the most popular one is carbon isotopes, right? We have carbon-12, carbon-13, and carbon-14, which is a radioactive isotope. It decays over time, and that's the basis for carbon dating, right? These are probably the most popular isotope. So all sorts of elements have different isotopes. An isotope means basically same behavior, okay? But different isotopes actually behave a little bit differently based on their sizes, right? So you add a neutron to something, it kind of slows it down, right? So they actually have different speeds and stabilities. You go into an element, and it's slightly different based on the isotope. So this is a periodic table of the elements where everything has been replaced by animals or things you might find on a farm. So if you look at just one category or one element, this is the category pig. You can imagine there's big pigs, medium pigs, and small pigs. And they're all pigs. They might all taste the same or behave the same, but they are slightly different behavior, right? The little pigs might run around a lot faster, and the big pigs like to sit in the mud and not do much, right? So that's just like isotopes. You can also look at the bear family. This is interesting. Just a total side fact for those who don't know. If you look at one taxonomic clade, they get bigger and bigger as you go towards the North Pole, and this is to decrease this surface area to volume ratio, so they lose less heat, right? So it's actually quite interesting in the bear family. The small ones, they don't hibernate. This is the sun bear or something like this, lives in Asian tropical forests. And we know the polar bear, the grizzly bear, the black bear, they all hibernate, right? So that's just like isotopes as well, right? The big ones like to stay in the spot they're in, and they don't move as fast. And the small ones like to run around a lot faster. So that's kind of the guiding principle of what we're going to be talking about today. Heavy isotopes prefer stronger bonds at equilibrium, and lighter isotopes move faster if they have to move through something. That's kind of a kinetic effect. Okay, so that's the background. Bears and pigs. I'll bring them up throughout the talk. And so we can use stable and radiogenic isotopes to understand what I like to call paleochemistry. We call it geochemistry, but really paleochemistry is kind of what it is. It's like a paleontologist uses bones to figure out things about animals that are no longer alive. A geochemist or an isotope geochemist uses isotope ratios to figure out things about chemical reactions that are no longer alive, right? So dead chemical reactions from billions of years ago, potentially. So stable isotopes, they separate based on chemical reactions, right? And you can use them to figure things out, like what was the temperature that a rock was formed at, how much of something happened, like how much evaporation or how much melting. You can use these equilibrium effects to get at reaction rates and mechanisms. And what people really like to do is use stable isotopes for source tracing. How much carbon in the atmosphere comes from fossil fuels? That is a question that's really easily answered with stable isotopes. You can see the signal, you can see the fossil fuels. It's really easy. This question, how much carbonate sediments are recycled into magmas? That's basically what we'll talk about today. But it's complicated by a few things. And radiogenic isotopes we can use for dating stuff. We won't talk about anything radiogenic today, but there is radiogenic calcium. And you can also use it for source tracing. Okay. So some of you might be wondering why calcium? Well, the real reason is because that's what my advisor studied when I was doing my PhD. But it's a great system. So first of all, it has a lot of stable isotopes, 6 of them. Most of it is 40 calcium. But really nice is that it has a huge relative mass difference. So 40 to 48 is about a 20% mass difference. So that means the difference between the little pig and the big pig is pretty big. In fact, it's the 3rd biggest after hydrogen and helium. So no bragging. Okay, so it's very abundant. It's everywhere. It's in our bodies. It's in the crust. It's in the mantle. 5th most abundant in the earth. Maybe this is just the crust, but it's in the top 5 or 6 most abundant elements. And interestingly, it's also got this radiogenic isotope, which we won't talk about today, but I do work on as well. 40 potassium decays to 40 calcium over time with a half-life of 1.25 billion years. Many of you have heard of potassium-argon dating. That's only 10% of the decays. 90% goes to calcium. No bragging. Okay. And what I like is that there's no redox effects. So things change oxidation state. That actually makes it a lot more complicated to understand. That adds a whole additional layer of complexity to deciphering the isotopes. So like iron, someone was measuring some this morning. iron isotopes. It gets a little complicated because you have redox state changes as well as everything else that also affects calcium. Diffusion, equilibrium, different stuff, right? Okay. And the nice thing in high T systems, we have actually a really big range of delta 44. So this is the notation for isotope variations. We have an 8 per mil range in high T systems. Biggest is in granulite phase schist minerals. And those are kinetic effects, which we won't talk about today. This is the notation. I'll say delta 44 a lot. That's what this means. So it's the 44 calcium over 40 calcium that you measure in your sample versus in a standard -1. So it's just if it has more 44 over 40 than the standard, you get a positive number. And if it has less, you get a negative number. And we multiply that by 1,000 and report everything in per mil with that with the symbol right here, which is like percent, but it has 2 zeros on the bottom. Okay. All right, so the overarching theme of the talk is understanding the deep carbon cycle. And so we all know in this room that atmospheric CO2 is sequestered in the oceans and is either as organic carbon or as carbonates, most often calcium carbonate, limestone, right? And then those sink to the bottom of the ocean, and then they can be subducted at subduction zones and basically go down into the mantle. So of all the carbon going down at subduction zones, it's thought that carbonates dominate the carbon budget. So this is altered oceanic crust. Here are all the sediments, some altered periddotites. These are mostly carbonates too. There's some organic carbon in there. And here's the little bit of organic carbon. Most of this is carbonates. These are the inputs. And these are the outputs, and they're incredibly poorly constrained. So people think maybe it balances, maybe it doesn't. It's hard to tell exactly what's happening. This stifled field here is diffuse outgassing, and it's very hard to put a number on it. So people use other isotope systems, like the famous carbon isotopes I told you guys about at the beginning, and you can measure that in CO2 and try and figure out how much carbon is coming from carbonates versus potentially other sources, organic carbon or other stuff. But carbon is incredibly sensitive to redox changes. It goes from -4 to +4 and everything in between. And so the isotope effects are pretty complicated. You can get some very big isotope effects just from phase separation. I read a paper yesterday that just came out. You're getting, 20 per mil effects just from phase separations in water, right? So the flux estimates are really poorly constrained. People say 50 to 90. I just saw another paper saying like 40 to 100. We don't know how much of the carbon goes past here into the deeper mantle and how much of it doesn't make it down and comes back up. So that's kind of what people want to use calcium isotopes to figure out. Okay, so because of the carbon problems, we try to use something else. So calcium isotopes as a carbonate recycling proxy. This is the fundamental basis for it. Here is basically just a histogram. On the top here we have carbonates, so marine limestones. And here on the x-axis is just too small to see, but that's delta 44 calcium, so the amount of 44 over 40. And this is periddotites, so the mantle. And you can see this is relative to periddotites, the carbonates are a little bit lighter in calcium isotopes. I say lighter means it has more 40 calcium relative to 44, right? So that's the basis people have used since 2011 when they started doing this. So it's not that old of a field. They've used this to try and trace carbonates. So this is delta 44 on the y-axis and 87, 86 strontium. I don't have too much time to explain in this talk, but this is samples of Hawaiian basalts. And they see this trend, and they explain it by mixing in a little bit of carbonate that has a light isotope signature and is heavier in 87, 86. Right? So they explain this trend by incorporating 4% recycled carbonates in the mantle that is then erupted at Hawaii. okay? So they think, yeah, carbonates make it down here, stored for billions of years, and then they come back up in volcanoes. The problem is that with stable isotope signatures, they're affected by processes. You can't just do mixing models. This is what we call a mixing model because you have a carbonate down here, you have a plume here, and you just mix along a line, right? But the problem with stable isotopes is that they fractionate. That's basically what happens when the little pigs and the big pigs separate. You can imagine if you had a pig stampede down the street, the little ones might make it to the end of the street first, right? So every chemical process fractionates stable isotopes. So the question is, do minerals and melts have different calcium isotope compositions? And if they do, you can't just use a simple mixing model to explain all this. You have to think about how much the isotopes separate at each step along the way in between the ocean, all the way down, partial melting and stuff down here, and then coming back up. It's a lot of processes. Okay, so when I got into this, there wasn't much known about it. And so we assumed at high temperatures, things should be at equilibrium and the fractionations should be relatively small. And so to kind of figure out what we were supposed to expect at equilibrium, I enlisted the help of Edwin Schaubel at UCLA, who Anat knows very well. And what he does is quantum mechanical simulations to figure out how much isotopes should fractionate between different substances. So it's all based on vibrational frequency differences, bond strengths, and bond coordination. Here is the results. So don't worry about the y-axis. Basically, high delta 44, so something that concentrates the heavy isotopes is up this way, and things that don't concentrate the heavy isotope are down here. And here's all the common minerals from 4 stories, so olivine, garnet, etc. So the order of the things that like the heaviest calcium to the lightest calcium are olivine, garnet, which is a high pressure phase, orthopyroxene, CPX, apatite, melt is right here, and plagioclase, which is a low pressure phase. So this is actually very exciting because you have a high pressure thing and a low pressure thing. They have different isotope compositions. So the range here at 900 C is about 0.8, and at mantle temperatures is about 0.5 per mil. Okay. And just for the aficionados, isotope people, we did verify these ab initio calculations using triple calcium isotope measurements, and you can ask me about that later. But it seems to verify those ab initio predictions. So quickly, in this talk, I'm going to talk to you about granites, then we'll go deeper, kimberlites, then we'll get more exotic carbonatites, and then I will give you a faint glimmer of hope at the end, talking about TTGs. Okay, so granites, most of the continental crust is made of granites. This is the Massif Central in France, where a lot of the samples for this study came from, the S-type. And granites are cool because they have low temperatures. You see in the plot I showed you before, the fractionations are bigger at lower temperatures. So granites are 700, 800 C. That's low temperature for igneous people. Okay, so we're on to granites. And we're trying to figure out, do we need source variations to explain the calcium isotope signatures? So that's the goal. And we looked at I-type, A-type, and S-type granites. These are basically igneous type, anorogenic, which I won't talk about much, special dry granites. And S-type granites, which are sedimentary type granites, and that's what people think is formed when you melt sediments. All right. And basically the idea was to compare data to models of calcium isotope fractionation. So this is some of the results. Delta 44 on the y-axis of all of these, and then SiO2, CaO, and MgO. These are tracers of magmatic differentiation. So partial melting and fractional crystallization make things go in various directions on here. And you can see that the arrows kind of lead to this fan shape. So we think there's probably processes affecting these things. All right, move on here. So here is some other graphs basically showing the same thing. This is so it's still delta 44. This is a proxy for garnet fractionation, dysprosium over ytterbium. So if you remove garnet from a system, it seems to affect the calcium, as we would expect, because it's concentrating heavy calcium isotopes. And here's europium. And this is the ASI index, which is basically a measure of how much aluminum is in a rock relative to other cations. And you get past this vertical line here, typically by adding sediments, siliciclastic palitic sediments with a lot of aluminum. So maybe there is a signal in these S-type granites. When you add sediments, maybe the delta 44 gets lighter, maybe it's carbonate. Okay, so I tried to cut this down because these are the most complicated graphs I've made. This is just the nicer ones. We did phase equilibrium modeling combined with the equilibrium calcium isotope values and came up with models that depend on bulk composition, evolving temperatures, changing mineral assemblages, compositions, and changing calcium budgets, recalculated at every temperature along a heating or cooling trajectory. Okay, and these are just the simple ones. This is melting of an enriched Archean tholite, which is a hydrous basalt. And you can see that all our I-type granites fit quite well the models. Interestingly, and kind of as we would expect based on the order of minerals I showed you in the calcium isotopes, there's a really good pressure dependence here. So it's not a direct pressure dependence, it's the fact that you get more garnet at higher pressures, right? So as the pressure goes up, the calcium isotope values go down. So it's a kind of a nice pressure proxy, indirectly, measuring the amount of garnet, basically. But the long and the short of this is that when you start with a basalt, which is this gray bar, you don't need any source variations to explain any of these, okay? They can all be done with pressure variations. All right, and the A-type granites I decided not to show because it gets a little complicated, but we are able to explain them with kinetic effects during plagioclase crystallization. And I'd be really happy if anyone asked me about that, but I won't kill you with it now. It has to do with the little pigs making it to the crystal first. Okay. Okay, S-type granites. These are, you'd think, pretty likely to have maybe carbonates in the source, right? So an S-type granite, maybe you guys have seen this kind of graph before. You start with the mud, say a mud up here, and as you cook it and increase temperature and pressure, it slowly turns into a shale, a slate, a schist, a gneiss. And if you heat it up enough, it turns into a migmatite, and that means it's partially melted. That melt escapes and forms what we call S-type granite plutons, okay? So that's how you make an S-type granite. You melt sediments. So the question is, do we need source variations in delta 44 to explain what we find in S-type granites? And so we made some models and show our data here. And we find that basically the answer is no. The variations are big, so you're getting down to minus 0.6 per mil relative to the bulk silicate earth. And if you're a calcium person, I apologize that we have 5 different standards we report to. But you start with this blue bar. That is your average P-light. And you can explain essentially all of these things. There's some variations in the bulk composition that are harder to explain. We're starting with a single composition. But importantly, you can explain the calcium isotope range this way. So we don't need any source variations, even in P-lights. And so, yeah, there's only 12 samples here, so a lot of this work has to be continued. The whole field really only took off, I would say, 10 years ago or so. Okay, all right, so that's it for granites. The take-home messages, after all that, is that delta 44 in an igneous melt decreases with increasing pressure. That's mostly due to more garnet in the source and less plagioclase, which fights the garnet. And because of all this, it actually turns out that lighter calcium isotopes are concentrated in the upper continental crust. Okay, so if you look at the continental crust, it's about minus 0.25, relative to the mantle, which is 0, and to basalts, which is oceanic crust, minus 0.1. Okay? So you're basically accumulating light isotopes here and potentially recycling heavier ones down here, whether you're melting the slab or just doing other stuff in fractional crystallization to make your granites. I don't subscribe to one model or over the other. You know, I did spend time in Switzerland, so fractional crystallization is big over there. But, you know, partial melting explains the abundance of TTGs. Anyway, average granite and granitoids suggest, you look at all those models I showed you, and many, many more if you look at that paper, the 2023 EPSL paper. But if you look at the average composition of granitoids in the upper continental crust, it suggests that they evolved dominantly at 10 to 14 kilobars, which is the lower crust. So most of the action is happening down here based on what we've seen so far. And then you extract melts from here and you place them up here and keep doing stuff. Once you get up to the high level here, that's when plagioclase crystallizes, and you can actually start driving the delta 44 back up. And that's a big reason A-type granites have positive delta 44 values. Okay. And this is no longer relevant since I took out this part of the talk, but it seems like there are kinetic effects that are pretty common during plagioclase crystallization. They keep having to be brought up to explain things. Happy to talk about it at some other point. Okay. Now we'll talk about kimberlites. So this is something I worked on with Andrea here, who invited me for the talk, and maybe this is why. Well, we're good friends too. So this is Kimberley, big hole. Kimberlites are called kimberlites because the original ones come from Kimberley, South Africa. They're really special magmas. They're the deepest source and second most CO2 rich of all the magmas erupted on Earth. I'm not thinking about lamprey and stuff like that. Okay, kimberlites. Why does everyone know them? Because they bring up diamonds. Okay, so this is a kimberlite diatreme explosive pipe thing, and they come from potentially 200 kilometers deep, and potentially much deeper, and bring up stuff from the lower, from much deeper in the Earth. Right. So they're very CO2 rich, alkaline, ultramafic melts.
Oh boy, man, I got bro. Man, I got hold up. I'm gonna have to.
Hey, Josh, we can hear you. We can hear you.
Oh, excuse me.
All good. All good. Okay. So yeah, they carry things from the deep Earth and explode onto the surface. That's why they have these carrot-shaped pipes, kimberlite pipes, right? They're really explosive eruptions, and they traverse through the crust at incredibly rapid rates. And I'm sure Andrea knows better than I do, but back when I was learning about this, some people thought potentially supersonic speeds to explain the size of the xenoliths that they carry up. I'm sure it's not supersonic, but it's very fast. Right? What's your, how fast?
2 kilometers per hour.
That's pretty fast. You're not allowed to do that in a school zone. Okay. Thank you. All right, so they're thought to rise at very rapid rates through the crust. I mean, if they're going that fast, they can go through the whole crust in like 2 hours, right? Okay, and then what else is special about them is that all except one of them are over 30 million years old. So something special was happening back then, or up until then. Okay, so the driving questions here is the same overarching question. They're really CO2-rich magmas. Do they incorporate recycled marine carbonates? Is that where the CO2 is coming from? Or is it primordial carbon that's actually already in the Earth in the form of graphite or diamond or something like this? And this is more for the geochemists. It's basically, do the mineral melt fractionations actually change at high pressure? Not just the mineral assemblage, but the actual fractionations. Do they change at high pressure? Okay, so I'll tackle that question first. And basically, I don't want to kill you too much with this, but here is a y-axis is bond length, CaO bond length. These are ab initio, some experimental stuff. And here's pressure. So what happens when you increase pressure is you crush things down, right? And so the calcium-oxygen bonds, which control the isotope fractionation at equilibrium, get shorter when you increase the pressure. The coordination also changes things, but you can't change the coordination in a mineral, otherwise it becomes a different mineral, right? All right, so this paper, which is Chen and some other people, they showed that garnet and CPX have very different slopes in the change of their bond length versus pressure, and claim that they actually cross over at some point, and that garnet actually becomes less heavy compared to CPX at about 7 GPa, which is potentially what kimberlites are coming from, 6 to 8 GPa. Then another paper came out just a little while after, and they said that the slopes were exactly the same, and that slopes depend on the coordination. So both CPX and garnet have 8-fold coordination of the calcium, and so the slopes, the bond lengths do get shorter with pressure, but they get shorter by the same amount, and so nothing changes. So no change, right? And this is irrelevant, but they actually don't have a figure showing the garnet and CPX for some reason in this paper. Okay, now for mineral melt fractionation, you got to think about the melts. Now melts are a lot more complicated, right? They don't have a fixed structure, and the coordination changes with pressure. So as you crush it down, things get more and more coordinated. You're actually coordinating up to 9 or 10 oxygens for 1 calcium as you increase pressure to ridiculously high values here. We care about the first right here, up to about 10 GPa. Right? But there's a big change in coordination. And the bond lengths change too. Here CaO is the dark blue. It might go up a little bit and then come down. So it's pretty complicated. There is a paper that just came out where they combine molecular dynamics simulations with ab initio stuff and predict a few of these things. Then it turns out they confirmed my suspicions, which make me very happy. I don't talk about that paper, it's too recent. Okay, so given the complexity in modeling the melts especially, we figured the best thing to do is measure kimberlites. Kimberlites come from 6 to 8 kilometers, 6 to 8 GPa deep, which is at least 200 kilometers, right? And so here is some plots, and you can ask Andrea why the delta 44 is on the x-axis, because he made them. But they all give the exact same value. That's the takeaway message here. So the CaO varies a lot, the MgO varies a lot, but regardless of all that variation, all of our samples gave this value of about minus 0.16 per mil relative to the bulk silicate Earth. Okay? And so I said, oh, this is fantastic. This is going to be a really easy paper to write. And so the question is, can we model this value using our pressure-independent estimates? Right? Does it work? And so we just picked 5 different possible modal mineralogies for the source. All of them had various amounts of garnet, olivine, CPX, OPX, and the carbon is inherent in there but does not affect the calcium isotopes. Here's our data, box and whisker, right? So this is the mean and the median. And here are the reproduced partial melting fractionation factors. And you can see that we explain very well, almost perfectly, given the uncertainties, everything with our 0 GPa ab initio calculation. So it basically suggests that pressure has an overall negligible effect on mineral melt calcium isotope fractionations. Okay. So back to the other question, do we need carbonates, marine carbonates? Well, the answer, I just showed you that we modeled it perfectly without the carbonates and without any pressure differences, so the answer is probably no. Of course, you get a reviewer that might want to force you to do a mixing model, and so here's the delta 44, here's the 8786 strontium. This is average Phanerozoic carbonate, so for the last 500 million years, this is the average of all the limestones in the ocean, right? So you got about minus 0.35 delta 44 and 70 something, 708 to 8786. You see, you can't mix this and that to explain the kimberlites. My laser pointer is dying, but that's okay. And here is a hypothetical carbonate with the most favorable conditions for potentially explaining this, and we barely touch the whisker on the box and whisker, right? We don't hit the box. So it's much more likely, this is how we imagine it, is we have two processes, mineral melt fractionation, that brings you down this way, and then you assimilate some of the lithospheric mantle to increase the 8786 and get you over here. So this is how we see it. All right. But of course, if you are a worrier like I am, you could think, well, maybe there's the pressure effects that are fighting against this unique melt composition of the kimberlites, and they equate to 0. Maybe that's what's happening, because the kimberlites have a lot of CO2 in them. I forget exactly how much, 15%? That sound good? 15, 20%, yeah. So we figured, well, we should measure something with even more CO2. So that's when we get over to carbonatites, which are the most CO2-rich magmas on Earth, okay? There's only one in the world erupting today. It's in Tanzania. And because they're so carbonate-rich, they're the lowest temperature magmas on Earth as well. So at 500 degrees Celsius, much cooler than a granite, right? And there's only one. It's in Tanzania, Old Enyo Lingai. And here's a picture of it, so you can see over 50% white stuff. Those are carbonates. And during the day, the magma is white, and at night you can see it glowing a little bit because it is still 500 degrees. So the question is, can we find recycled carbonates in the most carbonate-rich magmas on Earth? Well, if you ask some people, they would say yes. So here is a compilation of the data that existed before we did our study. 3 different papers, okay? One of them is MSLM 2020. This is all their data down here. So they found this average of minus 0.7 relative to the bulk silicate Earth, which is this gray bar here, and suggested, using that there was marine carbonates in all carbonatite. That's how you make a carbonatite. You subduct carbonates, and you melt them, and you make a carbonatite. Okay, so they said all carbonatites. And then another group came along and measured a bunch of carbonatites, and here's their data in the blue. And they found that they were all the same, plus or minus a little bit of bulk silicate Earth, and suggested you don't need marine carbonates in any carbonatites. 0. Okay, and then a third study came along, and they found the same average as this study, the second study, but they also found these excursions to some lower values here, and they said, okay, well, you need marine carbonates in some carbonatites, especially those after 300 million years, because they have 2 points down here. Okay. So we figured something should be done about with the fractionations, et cetera, et cetera. So there's large uncertainties in the fractionations. We have no idea what was happening with a carbonatite melts, right? It can't have the same composition as a silicate melt. It's totally different, right? And then all of these studies also assume that direct melting of mantle carbonates is how you make a carbonatite magma. Whereas a lot of people now think melt immiscibility plays a role. So you start with something like a kimberlite, and you fractionate things out of it long enough, you hit this 2 melt field, and you split off a carbonatite and a kind of silica undersaturated melt. Okay. So that's where the field was when we started this. This was also in collaboration with Andrea when we were at ETH. And so the driving questions were, could melt immiscibility be playing a role in these calcium isotope signatures that we saw? No one had thought about it and evaluated it before. Could kinetic effects be influencing the measured delta 44 calcium? I have not talked about kinetic effects, but I'd be happy to if anyone's curious. And can we fully explain all the carbonatite data without recycled carbonates in the sources?
I just have one quick question. Although the Odonio guy is noted as an alkali
Yes.
carbonatite, how much calcium
Is in that one?
relative to the alkali?
Yeah, we didn't measure anything from Oldoenio Lengai. But I guess that's the surface. Yeah, you should always ask Andrea. That's my my philosophy as well. Okay, good. All right, that way I can get through the rest. So basically, to answer these three questions, we took a threefold approach. We experimentally determined with these centrifuging piston cylinder experiments if silicate and carbonatitic melts have the same delta 44. We then measured some natural mineral separates, pristine mineral separates from a few carbonatites, apatite and calcite. And then we modeled the calcium isotope evolution of these things based on a melt immiscibility type of scenario. We also did direct melting, but I won't show you the results because I don't need to, because everything's explained with the melt immiscibility. But I'm happy to talk about direct melting too. So this is the centrifuging piston cylinder apparatus at ETH Zurich. It's unique in the world. It's in the group of Max Schmidt, right? And so you can do experiments at high pressures and temperatures and spin them at really, really high RPMs to separate out things of different phases. It's the only one in the world. And it's about the size of a shark tank. I always think of Dr. Evil when I see this thing. So you got a ladder that goes down here. It's about the size of a person. Okay, and this is what the ideal experimental result looks like. You have silicate melt nicely on one side and carbonatite melt nicely on the other side at the end of the experiment. First you let it exchange, then you spin it, and then you can just chop it up and measure it because they're pretty small. And here's the results. So delta 44 on the x-axis, nothing on the y-axis. And basically, you can see that in every experiment we did, the carbonatite melt is lighter isotopically than the silicate melt. And the difference is bigger at lower temperature, just as you would expect. And we have lots of, few at least, lines of evidence for isotopic equilibrium. And so here is basically the 1/t² relationship you would expect at equilibrium. You get the exact same fractionation factor for the three experiments we did at high temperature and the one we did at lower temperature. Okay, so it looks like the fractionation factor is about minus 0.21 between a carbonatite melt and a silicate melt at 1,000 Kelvin. And this actually suggests, because calcium is similarly bonded in a carbonatite melt as these other elements, iron, magnesium, zinc, strontium, barium, this actually should be the case for all those isotope systems as well. Some new papers came out confirming that you get lighter iron isotopes in carbonatite melts, and I think some of these other ones as well. Okay. So we did some more ab initio stuff. These are the quantum mechanical simulations, and basically, I won't bore you with this, but here are the apatite and calcite from natural samples, and they basically all agree with what we would expect for equilibrium. Right, so we figured we can model these things using equilibrium models. And the other thing is, all our natural data agree with the second and third studies, and not that first study that had all the negative values, which we think is an analytical artifacts. Something went wrong in that study with their measurements. All right. So again, I don't want to kill you too much with this, but basically we have a 4-stage model. First you melt the mantle, then you fractionate CPX, then you get carbonatite silicate immiscibility. Then you accumulate calcite from a carbonatitic melt, because carbonatite bodies are actually cumulates for the most part, right? Calcite and apatite-rich cumulates. And here are all the models for that. And I, pair up with people like Andrea and Max and just ask them how much of the calcium goes in each process, right? Here's the estimates. And you put it all together, and this is what you get. So you're starting, this is just delta 44 on the X, nothing on the Y. You start at the star, that's the mantle. Here's partial melting. Here's the CPX fractionation. Here's the melt immiscibility. Here's the calcite and apatite accumulation. And these are the results you get for the two different pathways, which are separating here. And here's the natural data. So you can see we get all the natural data, reproduce it quite well, starting from the bulk silicate earth without putting in any exotic carbonates. Okay, it's all done with processes, not with source fractionation. Okay, so the take-home messages, basically carbonatitic melts have lower delta 44, and we do not need subducted marine carbonates to explain the delta 44. It doesn't mean that they're not there, but it means that we don't need them to explain the calcium isotopes, at least. Okay. So this was kind of how the field started. You get your delta 44 data. That tells you the mantle source, delta 44, and then you just do a mixing model and get at carbonate recycling. But the revised framework should be something more like this, where you have your delta 44 data, you think about your source mineralogy, the amount of partial melting, melt transport where you could get kinetic effects, crystallization where you can also get kinetic effects, and then you can maybe get your mantle source, and then you can get your carbonate recycling. But you also have to consider other things, recycled oceanic crust, pelagic sediments, which can give you more garnet and affect the source mineralogy, and metasomatism by carbonatite melts, for example. These all play back into the source mineralogy so you can have an endless loop. So it's a little bit more complicated than people wanted it to be. And I used to end the talk around there, but I realized it was too doomsday-y. And so in this version of it, I decided to show you guys where we successfully applied that framework I just showed you and found what we think were carbonates. So we looked at TTGs, world's oldest rocks, right? The initial continental crust. And people use these to ask, when did plate tectonics start on Earth, right? So this is what they look like. They're basically granitoids, right? This is some of the oldest rocks in the world. And basically, we're wondering, can we identify recycled marine carbonates in the source of these rocks? This is what my advisor wanted me to do when I was at IPGP. But I was already thinking about this, right? And so I, first said, okay, but we should do some modeling first before we start thinking about carbonates, right? So I combined forces with my friend Chris Yakimchuk, who was a PhD student of Mike Brown at the University of Maryland and is now at Waterloo. He's an expert in phase equilibrium models, and we basically combined forces, and basically he does things like this. We have 3 different geothermal gradients. You're melting a hydrous basalt to make a TTG. And I come in and put all the calcium isotope stuff, and we come out with these models. These are 3 different geothermal gradients. You make the TTGs, hot, medium, and cold, 500 C per GPa. Right. So we have the models, and we just measure the TTGs and say, how do they fit the models? Well, they fit the 500 C per GPa models really well. So increasing garnet in this direction. And so basically, this is the exact same geothermal gradient you get at a hot subduction zone today. So it's quite possible that these were formed through subduction. There's 2 samples here that we can't explain, even with our fancy models. So we said, well, maybe that's carbonates. And these are the Nouveau-Agatuk samples, the ones I showed you a picture of at the beginning. It looks like they have sediments because they have a high paraluminosity index. Right, so here's the Nouveau-Agatuk samples that we can't explain. And they have other evidence for sediments. They have high 18O values, the 2 samples around 10. So that's pretty high. And there's other evidence for sediments. High 30 silicon, people have argued was oceanic chert. High iron isotopes, people have argued are carbonates. And metapelates are actually pretty common in this area of Canada. It's kind of in the north of Quebec. Okay, so that suggests that maybe there's 3 types of sediments in the precursors of these TTGs, Nouveau-Agatuk. And maybe that's crazy, but they're actually found together today very often in accretionary prisms if you go to Japan and ask these guys. So it's quite possible that something in those sediments had low delta 44 and high enough calcium concentrations to get those samples off our models, right? What has these 2 characteristics? Probably carbonates, right? But the average Phanerozoic carbonate, minus 0.35, This one, we need minus 0.125. So the idea we put forward in this paper is that seawater was probably more mantle buffered, and so you're starting out here, and you get the same fractionation factor, you get these carbonates that you can explain these TTGs with. This is modern seawater, and this modern carbonates. So this is what we put forward. People think this is the case for 87, 86. The mantle was a lot hotter. You have a lot of hydrothermal activity, so you're more buffering the seawater mantle value. The caveat that this can't be steady state. It probably wasn't steady state if you had 10 bars of CO2 in the atmosphere and you had to get rid of it. Anyway, okay. So here's the mixing models. For those who love mixing models, we got 3 N-member mixing models: shale to explain the aluminum, carbonates to explain the calcium, and here's the 2 samples. And basically, you need 30 to 50% sediments. That's along these lines. And one of the samples, 5% carbonates, and the other with 20% carbonate. So along with the geothermal gradients, which are the same as hot subduction today, we have some carbonates, and so we basically said plate tectonics was probably operating, or at least subduction was, 3.8 billion years ago, which is still debated. People love to argue about it. Okay, so just some conclusions now. 15 minutes. So the main overarching talk, the theme of the talk, could calcium isotopes be used to track marine carbonates in igneous rocks through this whole cycle, the deep carbon cycle? And the answer is yes, I think so. But it requires a lot of effort. It's not something that you can really just phone in and get an easy answer. Okay? There's a lot of fractionations. That's the issue. But luckily, there's plenty to learn along the way, right? So we're getting things like geothermal gradients, the amount of partial melting, the pressures that things happen at. There's lots to learn. And there's disequilibrium effects that can give you rates of various processes. All right, so the best approach to use if you're trying to do calcium isotopes, and you don't want to work with me, but please call me if you do, is do a full suite of samples from one location. That would be good. Then you would get a good idea of the processes. And use phase equilibrium models to then fit those data, right? And then if there's an offset required, maybe that's a delta 44 variation in your source, and maybe that's from carbonate. So with that, I'd like to thank you all. Here's some carbonates and a volcano. I did not take this photo. Any questions?
The entertaining talk.